Thanks very much. Thanks to the organizers, and thank you for sticking it out to the end of the day talk. I promise to be too enthusiastic. Part of my project here is to get you all excited about complexity. It's this idea that keeps cropping up in all these different scientific disciplines, and it's still, I think, very much, it desperately needs philosophers to come in and add some clarity and to see what these ideas have in common with each other and to what extent they're really capturing this more general phenomenon. So that's kind of in the background of what my project is. So an overview of what I'm going to do, I'm going to first remind you of the time-asymmetric law of increasing entropy. And I'm going to talk a little bit about statistical mechanics and the Mentaculus project. And then I'm going to give you some examples of increasing complexity. And I'm going to talk about 3 different frameworks we might use to try and represent this this trend of increasing complexity. A lot of this I will add is based on work that I've done with a research group that involves people, mostly scientists at Carnegie and Caltech and Rochester, mostly planetary scientists actually, who are interested in this idea of increasing complexity. So some of the work I draw on, especially on informational, functional information at the end, will be like, it's very much a product of this joint collaborative work. Okay, so you've all heard of entropy and the second law of thermodynamics. So this says that the entropy of a closed system goes up over time, right? This law is general, so it applies to any closed system. It's explanatory. It shows what processes you should expect, why you should expect them, and it's time asymmetric. So entropy increases towards the future and not towards the past. Of course, there are lots of caveats, and I'm not going to get into all the different ways we might define entropy, but entropy doesn't always go up. Sometimes it can go down, and in fact, we have good statistics for when it goes down and by like how often you should expect it to occasionally go down. So very rarely, the entropy of a system, a closed system, will remain the same or even decrease. And what that shows is the second law is the ballistic law. Another caveat is that when the entropy of a system is maximum, it no longer goes up, right? Because it's maximum. And so it remains constant and very rarely decreases. So this would be like the thermal heat death of the universe. Everybody likes to bring that up when I give this talk. So,
except that the universe is not a closed system.
Yeah, perhaps. Okay. Debatable, I guess. Okay, so what are some examples? If you have gas in the corner of a box and then you release it, it will gradually spread out. If you pour cold cream into your coffee, it will mix and they will thermally equilibrate to become the same temperature. The entire universe, arguably, is heading eventually towards a heat death of thermal equilibrium. Okay. So this is one of the kind of arguable success cases of reduction in philosophy of science, where we can explain the second law of thermodynamics. We can explain this trend of increasing entropy in terms of statistical mechanics. So why does the gas expand from the corner to fill the box? Well, here's how the statistical explanation goes. There are lots of different ways that the particles could be confined in the corner. And most of those ways, and the asterisk, of course, means that it's a continuous measure that we need, probably a big uniform measure or something. So most, maybe we can't count, but for the purposes of this talk, you think of it as most of the ways of being confined in the corner of the box go on to expand. Not all of them do. Some of them might just like bounce back and forth, or they might bounce around and then reconvene in the corner. But most of them fill the box. And so you can then conclude, and I think there are really interesting things to say about how the probabilities work and in what sense this is likely, given that the microphysics is deterministic. However, you can use this as a general argument to show why we should expect the gas to expand, how often we should expect it to expand, etc. Okay, so if the universe is a closed system, you can also apply the strategy to the entire universe. And you can say that if the universe started in a state of very low entropy, you can expect over time for that entropy to go up, ultimately culminating in a maximum entropy of thermal equilibrium. So the way that this works, I've described it, but more formally, what we need is a distinction between a macrostate and the microstates that can possibly make it up. So to do statistical mechanics, we use a 6n dimensional space, phase space. And you need 6 dimensions because you need 3 dimensions for the position of each particle and 3 dimensions for the velocity of each particle. And the number of particles is n. Very simple math gets us to 3n dimensions. And you can think of the macrostate as being something like the hot coffee. Here's some general description. In thermodynamic terms, you might mention the temperature. I'll talk about this a lot more, volume, etc. Now you have the microstate. The actual microstate of the coffee is some particular way that the coffee molecules are. So you can imagine, you coordinatize your space, and you say, okay, particle X, or particle 1 is at X, Y, Z. It has a velocity, momentum in the X, Y, Z direction. And you do the same thing for particle number 2. And you can fully specify that microstate at a time. And that's the actual microstate of the system. And you can plot it in phase space, the 3n or the 6n dimensions, 3 for position, 3 for velocity. Now, what's interesting about this is that there are, of course, other ways you could have a hot cup of coffee. Many, many ways that I've had coffee today. And what that means is that there are different microstates consistent with this macrostate. So even if it has the same temperature, it can have the same temperature. The average kinetic energy has to be the same, but that means you can rearrange the velocities a whole bunch of different ways and still have the same temperature. Same thing for the positions, right? The coffee molecules you can rearrange a little bit, and that's still what you might think of as the same macrostate because it's the same thermodynamically specified state. And so the idea is that you pick out a region in phase space corresponding to all of those different ways of being hot coffee. And then that will give you all the good predictions of statistical mechanics once you plug in the laws of the microphysics, the microdynamics. Okay. So one thing that I think has largely escaped the attention, so hopefully what I've said is fairly familiar, but one thing that I think has not been emphasized enough is that entropy does not increase uniformly throughout the universe. So as it's very likely to do in a box of gas or other standard examples that we see in thermodynamics that generally motivate our acceptance of statistical mechanics, that's not the case in general. Like in general, entropy goes up non-uniformly. And you might think, so take the example of a star. The region around a single star may uniformly increase in entropy, as all the radiation just kind of billows away. But the region around our sun does not, right? Why? Because the sun irradiates the earth and we get things like zebras. Zebras are not high entropy creatures. They're in fact extremely low entropy creatures. So biological systems regularly, thank goodness, reduce or maintain their entropy at the expense of global entropy. So you eat a bunch of low entropy food, you excrete high entropy waste, but by doing that, you get to maintain your delightfully consistent entropy. So I think that this is underappreciated. There's this robust trend for many subsystems in a variety of different domains to actually reduce their entropy over time. Okay, so there are these two robust trends. One, increasing entropy, the second law of thermodynamics, very familiar with that one. This other one, increasing complexity. So this doesn't show me what, yeah, okay. So entropy, you can think of as a measure of the disorder of a system. Complexity is not just a measure of order, there's other stuff that goes into it, and it turns out it's very difficult to kind of characterize satisfactorily, but you think of it as the order and the function of a system with a diversity of interconnected parts. The mouthful I'm going to hand to you for now. The standard examples, whenever you look up like, what's entropy increase mean? And then you'll see lots of great examples, like the gas, right? It starts in a corner and it spreads out. Temperature equilibrates, radiation. Examples of complexities increase. There's the generation of new atoms and molecules. So in the early universe, there was like very boring kind of soup of fundamental particles. Over time, right, we get more and more complex stuff coming into existence, more complex atoms. We get stars that take hydrogen, turn it into helium, and then you get explosions of stars that turn those into even more complex atoms. You get atoms combining on the surfaces of planets, for instance, and that creates a whole bunch of molecules that never existed before. You get things like geological processes, like earthquakes, volcanoes. Biological evolution started very simply. Still don't quite know how, but then over time, you get something like a zebra, much more complex than a single-celled initial organism or whatever the first thing might have been. In brains, you see this neurological development happens over time, over species generation. It also happens developmentally. Right? Your brain gets more complex as you develop in a womb. Technological development has also seen this kind of increase in complexity. My iPhone, extremely, that compared to a stone axe or whatever the state-of-the-art technology was, much more complex. Okay, so just a plug for some other work I've done. I actually think that the project of reducing the asymmetries of records, memory, influence to the entropy asymmetry that you might be more familiar with, people might say something like, oh, entropy, the direction of entropy is what gives us a direction of time, right? Or the reason we think time is directed is because of the entropic arrow. I think that the important explanatory work is actually done by complexity asymmetry, which I would like to probably situate between the entropic asymmetry, and maybe you need other assumptions like a high enough combinatorial space in the beginning of the universe, something like that, in addition to this entropic asymmetry, and the right kind of fundamental forces that we were lucky enough to have in the universe. And then once you have the complexity asymmetry, that's the thing that actually allows for formations of memories and records, things like that. Okay. So I'm not going to argue for that now, but I'm happy to chat about it. So you might wonder, you just said these two inconsistent things. You're all very smart. It's probably you saw this coming. But I get this question a lot. Well, what do you mean that if the entropy is going up, it can't be that it goes down too? And of course, the resolution is that the entropy can only go down or maintain when it's an open subsystem, right? So like I was saying about you eating the low entropy food and excreting high entropy waste, like once you include all that, I'm not like decreasing the entropy. I'm actually like increasing the entropy of the universe in order to keep my entropy low. So it's just like a refrigerator. You can't keep yourself cool by just like opening it if it's inside your house because all the waste energy like heats up the rest of the room. So if we're going to be careful, I think the better way to put it is the entropy of any closed system goes up, but the entropy of some open systems goes down. Of course, not all open systems, but some. Okay. So I think that this is a robust, interesting fact about our universe that applies across a bunch of different domains. And so I think that we ought to call it a law in the same way we call the second law of thermodynamics a law. It's not fundamental. It's not like, direct, like, some people who are in the sciences often will say things like, oh, it's teleological or it's an exception to physics or things like that. I'm not saying anything like that. I'm saying it's a law in the very same kind of sense, the second law of thermodynamics. There are all these analogies. Time-asymmetric. So if you look at the history of the universe, over time, things get more complex. I think it's explanatory. this law can explain why we should, I mean, I think it would be surprising if things got more complex in all these different domains for no reason. It was just like a happenstance. So I think it should be explanatory. It should be general, so it should apply to all these different domains. And reducible, that would be great. I'm kind of a reductionist at heart, so that would be cool. I don't yet see how that goes, but that, you know, lots of people are much smarter than I am. So I think that this law should be consistent with fundamental physics and the second law. Right? So what I was saying before, this is not an extension. And ideally, it'll end up being quantitative. So it'll give us things we can experimentally verify in the same way the statistical mechanics is done for some cases. And I think the way that statistical mechanics did it is you had examples where it worked really, really well. And then you said, and so on, right? For the much more complicated cases. And so you have kind of like a, you know, it's reasonable to assume that maybe something like that is working in the general case. So I'm hopeful that there's something analogous that can be done for complexity. Just like work it out quantitatively in some simple cases in different domains. You say, and so on. Okay. So what are some candidate laws of complexity? So I have heard many people say the Mentaculus does this. So I will talk about what that is in a moment, but the idea is that the increase in complexity is a consequence of statistical mechanics plus a low entropy boundary condition. And that this has already been done. I'll argue it is not. Assembly theory is another approach that tries to solve this, and the idea with assembly theory is that complexity is a historical measure of the minimum number of steps it takes to build something, and it very much relies on an idea of like logical space of combinatorial possibilities, and the increasing complexity is a consequence of the way that small things combine to form bigger things. Functional information, this is the one that I've been involved in the research group with, and the idea here is that complexity is a measure of the proportion of states that are functional, which means they persist, and that increasing complexity ends up being like a consequence of the dynamics within the relevant phase space. So it's a schema presumption. There are a bunch of other frameworks. So if you look at the literature on complexity, as I mentioned, it's very, very difficult to wade through. So again, my plug, like if you think that there are better things that could be said about, you know, evolution in biology, something like thermodynamic engines, Jeremy England, maybe some of you have heard of, informational complexity and transmission of signals. These are all kind of different approaches in different domains that have tried to tackle this idea of complexity. I'm not going to talk about those today, but that's not to say they won't work or couldn't. Okay, so how does the Mentaculus account for complexity? When did we start?
Yeah, 22 minutes.
I have 22 minutes left. Okay. Okay, so the Mentaculus is a proposal by David Albert and Barry Loewer, and a ton of other people have contributed to this general project. And the way that this proposal goes is that you impose as a posit or assumption of the theory that there is a low entropy boundary condition, just so I call it a past boundary condition, and that explains this overall increase in entropy. They think it can also explain not only the universe's increase in entropy, but also the increase in entropy for any subsystem that goes on to exist. And that's controversial, whether or not that works. They also claim that it can explain every macroscopic law of the special sciences. So in principle, this framework, they claim, yields probabilistic predictions for every formulable proposition, what Albert says. For now, I'm just going to focus on the special sciences. So regularities like zebras eat grass. Okay, so Albert and Loewer have no explicit discussion of increasing complexity, but I think if their framework's successful at explaining the special sciences, there's reason to think it can explain kind of like multi-domain trend of increasing complexity. So it happens here, it happens there, it happens there. Why? Because these are all predictions or consequences of this one framework. Okay, so I'm going to argue that the idea of a macro state for the special science kinds is still underdeveloped in a way that does not let them yet claim this as a result. So here are the three assumptions. There's deterministic Newtonian microevolution, and they're asterisked again because there are ways of modifying this if the microdynamics are different, like quantum or probabilistic. And those dynamical laws describe the evolution of the fundamental particles. There's a past hypothesis. This is the low entropy boundary condition. That is, the universe started in a macro state of very low entropy. And when I say started, maybe a better way to put it is the minimum entropy of the knowable universe. You know, maybe before that, can't really make claims about that yet, as far as we know. But at some point, this minimum entropy of the knowable universe was very low entropy, and it was roughly, at the time of the Big Bang. And then we add the statistical postulate. So each microstate, remember, each way that it could have been in that very low entropy, compatible with that past hypothesis is equally likely. Again, the equally likely is the uniform measure if it's a continuous space. And the idea is that these three things get us everything we could want. So why do we do this? Well, a uniform measure over all the microstates compatible with a macro state, if you just did it at this point in time, you'll get great predictions. You'll get terrible retrodictions because a uniform measure over all the ways of being in a corner, very much likely to have been higher entropy, very much likely to will be higher entropy. So what they do is like say, this is wrong because we're going to constrain the whole universe to be very low entropy back here. And so very low entropy back here says you get to here before you get to here. So this is very unlikely to produce this. Where there's nothing built into production more than the dynamical behavior of the microcosm. Okay, right? So essentially, what they need to get those forward-looking predictions to be good predictions, is for the macro state that we think of as associated with something like a box of gas to be highly fibrillated. Never remember which way that is. Fibrillated. And the idea there is that you don't look at all the microstates consistent with being gas in a corner of a box. You only look at the fraction of those microstates that came on trajectories that were initially in a very low entropy initial state. By the time they get to the macro state, there are only a few of them, a few subregions that you can think of as picking out the right subregion. And if you like thinking in trajectories, you can think here's the low entropy boundary condition, here's the gas in the corner of the box, here's the gas spread out. And the idea being that these all have the right predictions, including the yellow ones of what goes on to happen. But without the past hypothesis, they make bad predictions. And probably I should have drawn the yellow ones as coming back to the same macro state of being spread out. Okay. So the idea here is that by putting in the low entropy boundary condition, you get all the right forward-looking predictions because you exactly replicate the predictions of statistical mechanics for that macro state that you're considering at a time, like the gas in the corner of a box. You don't want to get the bad retrodictions, but you want to get the good predictions. So their claim is that this uniform distribution that's constrained by the low entropy initial state will yield all the exact same predictions as the uniform measure of that macro state towards the future. Okay, so you might think, well, hold on, what is a macro state? How are we picking these out? And I think this is, there's a lot to unpack here. This is from Albert, and he thinks, okay, so you carve up the world into these sets. So one way to do it is you can use everyday human language. You can use discriminatory capacities of your unaided human sense organs. You could use simple and autonomous and robust and non-trivial dynamical science. And the essence of thermodynamics that these three carvings happen to amount to more or less the same thing. Okay. So I think that that's just wrong. I don't think that those three things amount to at all the same thing. And that's part of why I think this can't work for something like complexity. Because the kinds that we're picking out in complexity, the stuff that interests us about complexity, are things that are not thermodynamically specified. So being a zebra, special science macro state or kind or whatever, is just not sufficiently characterized using only thermodynamic properties. So when you characterize something in thermodynamics, you give things like its temperature, its volume, its pressure. But of course, volume looks really easy in phase space. Why? Because it's done in terms of positions, right? And that's just one of the, those are three of your axes right there. Temperature is done in terms of average kinetic energy. What? That's just your momentum, right? That's your other dimensions you've got right there. So it's natural that that space is a perfect fit for thermodynamic properties. And you get exactly the right kinds of regions, they're well behaved, uniform measures seem to do exactly the right kind of thing. To see this, just imagine what would happen if you took a uniform measure over microstates compatible with a thermodynamic specification of a zebra. So you're gonna just give me its like thermodynamic properties, its temperature, its pressure, its volume. Well, it's gonna like immediately equilibrate, right? Because you haven't told me anything about, whether it's got DNA, whether it's breathing, whether it has like internal organs, nothing like that, right? So a mere thermodynamic specification is going to give the same predictions that you get from thermodynamics, which is it's going to blur. So you're like, well, don't do that. That's silly. Don't characterize it that way. Maybe there's a better way to modify this region in phase space. And in fact, this is what I've been told they would like to do, right? So you can't just do it so simply. You should do something else. So you might think, okay, well, being a zebra, like look at the other stuff Albert said. So maybe it depends on our language. Right? So maybe you pick out in phase space anything that you would like call a zebra, or anything that you could discriminatorily get with your unaided sense organs. I'm going way too slow. No, I still have. Okay, 12 minutes. I could definitely. Okay, but that's not going to work, right? Like just what I can see with my ordinary unaided eyes, like that doesn't get me DNA or anything like that. You don't want to be. Okay, so great. Uniform measure is not going to work. I think that this all has to do with the failure of characterizing macro states. A uniform measure over these states, you might think like after you conditionalize on the past hypothesis, maybe it will. So maybe there's something more that happens between like conditional. So in the case of normal thermodynamics, conditionalizing on the box of gas did nothing, like adding the past hypothesis did nothing for us going forward, right? It yielded exactly the same predictions. But maybe there's more that's going to happen now when we're talking about zebras. So maybe you conditionalize on the thermodynamic properties of a zebra and the past hypothesis, and now you end up with different predictions than you get from just statistical mechanics of the present macro state. I think that could be. It does seem kind of plausible that, if you happened upon an alien zebra, you would not think it had kind of coalesced like a Boltzmann brain out of the thermal chance. It was probably evolved on that planet. So maybe that suggests there's something crucial about the fact that it's so complex that gets you from the past hypothesis through the macro state, but it won't get you everything, right? So this will exclude all these kinds of hard-won scientific information, like it'll get you phenotypic generalizations about how things look, but not the genotypic classification of the clades. So maybe we should do this. We should say the right macro state is, whatever our best science says a zebra is. Only things that count, according to our best science of what a zebra is, should count as like one of those macro states, microstates consistent with. Okay, so it may well be that once you take a measure over this like very, very highly filabrated region in phase space, you will get all the regularities of the special sciences. So maybe that's right. I kind of hope that's right. But there's some problems, right? So one thing is it's circular. If you thought the special science laws were going to kind of fall out of the Mentaculus, now you have to take your best science to use it to specify the right things to be conditionalizing on. Also, if you fully specify these, you're going to need microscopic information. And the whole point of using macrostates was that you didn't need the microscopic information. Once you have the microscopic information, maybe there's no point to do these measures anymore anyway. The other thing is there's just kind of like no empirical upshot to this. It's a kind of just so story that may turn out to be true, and I kind of hope it does, but it's not going to give us any kind of quantitative reason for why complexity goes up over time. Kind of like, well, if everything works out just so, we can see that, it will, but, kind of a proof of consistency, I think, rather than an empirical predictive tool. Okay, so what's another approach? This is kind of a fun one. It's one that I think philosophers can definitely latch onto very quickly. It's assembly theory. And the idea here is that complexity is a historical measure of the minimum number of steps it takes to build something. So basically, you get big things from little things. And the assembly space, when you look at the assembly space for an object, you have the elementary building blocks and you have the elementary operations on blocks. So basically, which binary combinations are possible. And what that allows you to do is to characterize any object in terms of its assembly number or index, which is the minimum number of operations it takes to get there. It might have taken more actually to build that thing, but that doesn't matter for its assembly index. And then you need also to keep track of the number of copies of how many of those things you have. So here's an example of just the assembly of this diethylphthalate molecule. And it has an assembly index of 8, because you can see first you had to take these building blocks and assemble this, then you had to take these and assemble that, and you had to take this and this, So you can see how over time you had to do 1, 2, 3, 4, 6, 7, 8 assembly steps. So this molecule is a bit complex because it has this index of 8. And that's how you know how complex something is. You just read its assembly index. So that's kind of cool. It gives you at least a number to associate with an object for how complex it is. And what happens to have been assembled will constrain what future possibilities there are, right? So as you build things, they can be used to build other things. But before you had that, they couldn't. So this is the reason why we all have DNA. It's like at some point, DNA assembled, and now we all get to benefit. It didn't have to kind of get rebuilt each time. It was already there. Okay. The number of possible objects grows super exponentially, and all that means is the exponential curve can have extra curves in it, depending on what gets built. And so you can see how in the middle, these are the things that are actual observed structures, and then they kind of allow for additional building that could happen. All right. So let me just say that one of the other things you have to keep track of for assembly theory is the domain. So you might have thought, well, hold on, those didn't look like fundamental particles, right? The positions and velocities, the building blocks, these things, these are already atoms. They're already blocks. So, or atoms. So you might worry, right? There's something going on that it's domain specific, and the assembly index is now a domain relative feature. I don't know that that's a bug or a feature. I kind of think that's a feature. And then what you need to do is then relate the different domains to each other. Because of course you couldn't compare the assembly index of a molecule that you had just figured it out for with an organism and their DNA combinations, right? those are, the DNA has many, many molecules making it up, and the other molecules. Okay. Here are some of the problems. It's like very difficult to read this carefully as a philosopher. So they say lots of things. Like they think they're capturing the degree of causation. They say they have a new aspect of physics that's emerging at the chemical scale. They're defined by the histories of formation as an intrinsic property. They're anticipating the theory to be sufficiently general to apply to like a bunch of stuff, all these different things. And they're going to just throw in, right, like human languages, memes. So I think this is my appeal. Like if you find assembly theory interesting, you should wade in and tell them that, like, well, not tell, you know, whatever. Figure out the better way to use these terms or to figure out what exactly it is that they're claiming, because it's difficult to parse sometimes. All right, I'm going to now present the approach that I think is really, really interesting. And this is the one I've worked on with the group. And it's called functional information. So I hate this title. I hate what they've called it, but I was one of many co-authors, so I couldn't persuade them to change it. I think the information itself is multiply ambiguous. I don't know if any of you tried to figure out what information is in science. There's not one notion. Okay, so according to this theory, the complexity of a system is going to be given by a quantity calling functional information. This is going to be the fraction of combinations in the relevant state space that are functional. And by functional, we just mean persist for the purposes of this talk. And then complexity will increase where there's selection pressure for a function. So here's the paper that we wrote on the rules of function selection involving systems. It's got a bunch of views already, like 90,000 downloads. It's funny as a philosopher, you publish in science, you're like 90,000 downloads. And you get a lot of emails from people who are like, I too have solved complexity. Okay, so I encourage you to check out the paper just to see kind of what it's like. There's another philosopher who's a co-author as well, so it's not, you know, some of it, you'll see like, we need a context here. It's context dependent. You're like, philosopher wrote that. Okay, so the complexity here, this is the equation, the general equation. And the idea is that E is going to be some specified function. So you say like what it is to be functional. So you have to define that. That's an input. F sub x is the fraction of configurations that are able to do that. So it may only be that like some DNA permutations are functional as a zebra, and those have to be inputted. I is going to be the functional information. And then the law of increasing in complexity says that the functional information, so the I, goes up if many different configurations of the system undergo selection for one or more functions. So as different proportions of your system are able to meet this function, then you get the increase in complexity. So the idea behind this is that it's general. So it's a general schema that you can characterize complexity in a bunch of different domains. So you can say like, all right, what are the possible permutations of the system? I think we should also add a probability measure over those and say which of those are more likely, because some, of course, DNA permutations are much more likely than others. And then in the environment, so it's context dependent, relative to an environment, which of those are going to be functional in the sense of surviving or persisting or reproducing or however you want to define it. And then that means that you can basically take it as a general thing, like increasing entropy, and say, what does that mean for an engine? What does that mean for temperature differences? What does that mean for all those? You can do the same thing here. So each domain has its own state space where what counts, it tells you what counts as a combination. And then each of those domains has its characterization of what counts as functional. And so it's scientifically deferential. It appeals to like all these different sciences to fill in those schemas, and they get to use their own concepts. So in that sense, it's going to be circular in the same way that you have to appeal to the science to get the right answers. So it gives you the time asymmetry. So it'll tell you why these selection pressures lead to more complexity over time in all these different domains. And it will also, or it should also explain why complexity sometimes decreases, right? So during a mass extinction event, none of the permutations are able to be functional. And so that will be a result of using that kind of schema. So I think that another cool thing to look into is to decide to figure out like how these different state spaces. So it's kind of like take this really cool idea that we had in statistical mechanics of the phase space and all the trajectories and doing a measure over those. Do the same thing, but in a different domain with different kinds. So you say, now we're doing it over DNA strands or different atomic combinations. And then you can do a measure, it might not be uniform, it depends on the space. And you can see which ones of those go on to be functional. And then if you can relate those spaces to each other, you know, that's the dream. You've got like a full theory of all the special sciences. So perhaps the Mentaculus and functional information can both be true. And maybe there's a way of reducing some of this stuff to that, but maybe not. I don't know. Okay, so thank you.
Keep your hands up. Yes.
Yeah, thanks, Heather. That was really cool. So you mentioned kind of at the start, and you came back to it later about how this would relate to the second law.
Yeah.
But I think that one thing that a lot of people were trying, including Albert and Loewer, and certainly lots of people before them, like Reichenbach and this lot, is relating things like records and causation quite strongly to the notion of entropy.
Right.
And what some people have tried to do, which I mean, me included, is like try and split things so that you can still have that. It might not be. It could be that what the second law does, and having that kind of entropy gradient, what it does is it might not explain all the other arrows directly, but it might just give you a climate in which interesting things can happen. You don't just have a boring heat depth, right?
Good. Yeah,
Yeah.
Perfect. That's a great question. And I didn't say this at all.
Yeah.
So yeah, I do think that the fact that entropy is going up is a prerequisite for any of this.
Exactly.
Right? Yeah.
Yeah.
I don't think yet that people have done enough to explain why that alone leads us to expect complexity. Yeah.
I mean, the thing that might kind of finish the explanatory job, for instance, might be something more to do with the character of the initial distribution, because you've got all these people in like Arnsenius and Horrich and a bunch of people, and they've basically said in Pearl something like a simple initial state or a lack of correlations or its genericness or its flatness or something along those lines. And what it gives you is it gives you some kind of time-asymmetric probabilistic structures. So for instance, the forks of the fork asymmetry, like those things, but not those things. And that looks like it's kind of germane to the complexity asymmetry, because if you're getting a causal asymmetry, that could that sort of seems more in the ballpark.
So I'm not as familiar with those authors as I am with David Albert and Barry Lower's attempt to explain, but I think that's exactly right. The idea was always, if you start with this low entropy state, you just plug in the dynamics. Now we get everything like memories and records, and that we get counterfactuals and causal influence and all this other stuff. And I think that the missing piece is between the thermodynamics, which is very well argued for. And people like to argue against even that in the view. Like I don't know, do you get that like gas could ever start in the corner of a box and be likely to expand as a subsystem, right? You need other assumptions, maybe of mixing and things. But it seems that if you get that, my objection is that because the goal was always to just reproduce the statistical mechanics predictions, there's no guarantee that you'll get the kind of non-statistical mechanics. And so so it may well be that if you make the initial state more complex, you put in like the specific interaction laws and you put in like the inhomogeneity, and that there's enough combinatorial richness of some kind, then you'll get it likely. And I think this is what maybe Jeremy England is trying to do in terms of just using thermodynamics.
Can I do a follow-up? Is that cheating?
Maybe we can follow up
We'll
after.
do it later.
Okay.
I apologize, I don't know everyone's name, but the next question is all the way at the end. Thank you, Heather.
Yeah.
So I like the Mentaculus. and was moved by the objection, the circularity objection, if we were to appeal to, whatever scientists say zebras are, they're going to have, because we're supposed to get the regularities, loss of regularities for special science of the Mentaculus. But I was wondering if that's going to be a problem too, if you were to combine the Mentaculus.
Yeah.
Because you guys are going to be differential as well, right?
Yeah, I think.
Yeah.
Yeah, I think that the deference that I like is kind of wearing it on its sleeve. So I think that that's, I'm just embracing that. So I think if the Mentaculus defenders wanted to say the right way to characterize a macrostate is to ask like a genetic biologist, whatever, what's a zebra?
Yeah.
And then figure out what that corresponds to in phase space.
Yeah.
And then you do the uniform measure. Maybe that gives the right result. I kind of think at that point, the space is going to look so bizarre. It's no longer kind of a well-behaved thermodynamic region, but like, you have to pick out what counts as having DNA and all that other stuff. That it kind of seems hopeless and as any kind of useful or empirically grounded. And again, it's not to say it couldn't be consistent. Like it may well be that the uniform measure over those states in phase space. And I think they would say something like, well, it hit better, like give the right probabilities, and maybe it hit better. And maybe we can hope that it does. I just don't know that there would be any way to actually verify that.
So the functionality helps in that you are not appealing to anything basically macrostate-ish related.
That's right. It's kind of like, I'm going to use this different phase or this different state space and the different dynamics. And if you think that there's a connection between them, then that's what has to be argued for, rather than like trying to do it all in phase space. Yeah.
Jeanette.
I'm not asking a question. I think I lost the thread of what you were trying to do.
Okay.
So one of the desiderata that you had at the beginning,
Yeah.
something to be involved, was that it should be general.
Yeah.
And then you brought in the analogy with statistical mechanics. But so, and this is a genuine question: how general is the law of increasing complexity? I mean, all of your examples were drawn
Right.
from biology, and I would have thought that
Yeah.
in that case, what's so remarkable about biology, I mean, from
Yeah.
a physics point of view, is precisely that you've got all of these complex systems. And the natural way of explaining that is that we've got a selection mechanism. So what's happening is the world is throwing up configurations. It's selection is acting on emergent functionality. So you wouldn't expect some bottom-up general explanation
Right.
of why you should expect for any physical configuration that there should be an increase in complexity.
Yeah.
I mean, and all of the theories, or at least ones I'm familiar with, like assembly theory, for example, are trying to say that once you've got a natural a mechanism for selection going on, then you can explain the dynamics of selection as leading to increased complexity. And it's essentially a historical story.
Right.
And it requires time, it requires the operation of selection. So there's no bottom-up story. That analogous to StatMech, where you could look at the physical laws and say, oh, I can see looking at the state space and the dynamics on that,
Yeah.
that you would expect some emergent.
So, okay, so I'm not totally sure about the bottom up part of that question, but one thing I do want to comment on is that most of the people in the group are planetary scientists. And so they're really persuaded by this idea that there are some structures that are very stable and other structures that just kind of like come and go. And so, it's like some of the systems we've analyzed are things like, the sand in a river, and how if you have a certain kind of flow, you start to see these ripples. And then those are kind of reinforced by the continuing flow, and they're also self-reinforcing. And so you might think that's, in terms of function, you just say persistence, and then you say, do the ripples persist? And under this kind of flow, they do. Under that kind of flow, they don't. If they're made up of this kind of composition, they do. If they're made of that, they don't. And so I think that's the part and you might think, well, persistence is kind of boring, or maybe the part that's really interesting or needs to be more argued for is like, how does that get more complex rather than just persisting? And then you're right, the selection becomes crucial. And the idea being that, certain atoms are selected for in the sense of, those are the, like, when helium's generated, it lasts for a while, so it persists. And you have the generation, and then you have the persistence, and then that's how you get, yeah, okay.
All the way to the back.
So for a various subdisciplines where complexity is tied really closely to novelty, things like emergence or dreaded panpsychism. Is there any hint of that in the stuff that you've been looking at?
Yes, so I didn't mention it because I mostly just wanted to motivate that there is this general trend of increasing complexity and we need a theory of it. But yeah, actually at the end of our paper, we talk about novelty generation as kind of like the ultimate of persist. So like you can just persist statically, and there's dynamic persistence, and then there's generation of novelty, and that those are all going to be really important ways to help characterize this. So yes. Yeah. Yeah.
Thank you.
Thanks. Yeah, until Moore's said, specified about exactly what complexity is and exactly what the language is, then I'm not really sure I believe that the world is getting more complex. There are many ways in which it's not. So, for instance, I know of a study that defines a well-defined notion of complexity and applies it to rock music. It shows that, I'm sorry, because most of you are younger than me, but rock music is becoming more. And so on this measure of complexity from the 70s till now, complexity has been going down.
Yeah.
And so is that a counterexample to your thesis?
Yeah,
I mean, so,
probably. I think,
but
yeah.
presumably that's a different measure of complexity that you're using in biology,
Yeah.
which I think, the sponges that are evolving right now are probably projecting as well. And they're getting a bit evolution in the
Totally, yeah.
But
Yeah. So, yeah, great. There are really good examples of, complex. So historically, sharks, I guess sponges that last forever with the same body plan and don't change at all, but they're very functional, right? And you might think they're not getting more complex. Meteor kills off a bunch of mass extinction event. There's like a big decrease in the complexity. And so part of this is, do we need a new concept to like capture this thing? And I would say that because you keep seeing it over and over in all these other sciences, it's like some prima facie evidence that people in general think that there's this notion of complexity, and that over time it's gone up in terms of like all these different domains in general in the universe. But I think just like statistical mechanics, it can't be that your second law says entropy always everywhere goes up, because we know if you have a small enough box of gas, it'll eventually go down. And so it might be a probabilistic thing. It might also just have to include more details about when complexity goes up. If there's no selection pressure, you might think there's going to be no inferences we can draw about whether it'll go up or down. So I think that in some sense, as a philosopher, in part, we want to capture this intuitive idea of like, well, yeah, gosh, look around, like we're more complex than a soup of protons or whatever. Maybe not. You don't think so? You're not sure? Okay, yeah, I mean, I think part of this project has to be being precise about what complexity is. And part of the problem of trying to engage with these scientists is that they all disagree with each other about what it is. And so I don't know what particular measure they were using for rock music or how that would tie in with some of these, but I think that that's exactly one of the open questions. And I think in my mind, it was like either, entropy could have gone up uniformly, like when I picture all my thermodynamics examples of like a box of gas just expanding forever, but it didn't. It went up, entropy went up in this way where subsystems became very low entropy relative, open subsystems relative to their surroundings. And I would want an explanation for like why that is, and it might be domain specific for things that are as complex as us in order for me to understand why.
Chris, go for it.
Yeah, no, I just wanted to comment if you have heard of the Prigogine idea that increasing complexity is like a way of systems to get faster to thermodynamic equilibrium.
Yeah. So I think this is related to the thermodynamic engine idea. And that, as systems get more complex, they're better at converting, ordered low entropy into high, right? And you can see that with humans, right, consume a lot more order, produce a lot more waste than other things. And so there's a question of like, so I have heard people say things like that, and then you want to know, like, you know, in order to, like, it sounds, and oftentimes people will embrace that side of it, say it's in order to. It's like a teleological idea of like, we're all trying to increase the, you know, the heat death, bring about the heat death of the universe as soon as possible. And you might think that because there are humans around, it actually will happen sooner than it otherwise would have. But then I think as a philosopher, I want to be careful about, like, do I really think it's goal directed or something like that? And I would say I'd prefer something that doesn't appeal to that. Yeah, but if you just say, like, in general, systems have tendencies to increase entropy as fast as possible, and the more they do, the more complex they are, then that, yeah.
Yeah, because I was thinking of simple systems, like if you have a system of particles and you have gravity forces, then the entropic arrow is like aligned with the complexity of it. We think that a star is more complex than particles or dispersed in space. So maybe.
Yeah, and it's also, you have to be careful too about how you're counting the entropies and how you're doing systems.
Yeah.
And of course, you know, if you drop a bomb on a city, dramatically increase the entropy, but like you didn't increase complexity. So it can't be like just as straightforward as a direct connection, but these are well-known kind of examples. So yeah, it's yet another approach to complexity that we should all be looking at.
Thanks. Just first a note and then a comment.
Yeah. Yeah.
So first, I remain to be convinced that we should call this a law.
Yeah.
Increasing complexity, because a law would normally be an exception unless you have some truth or something like that. That it cannot be, it seems. Now, the second law of thermodynamics, of course, is not exceptionless either. It's still called a law.
Right.
But is the law of increasing complexity really as high probability as the second law of thermodynamics? And it seems to me there are reasons to doubt that. Yeah. Of course, again, it will come down to exactly how we think of complexity. It seems to me that we can certainly come up with notions of complexity on which complexity will counter an increase in entropy rather than go along with it. Then it becomes really questionable how general that's going to be. So I don't doubt that there's a very general and interesting class of systems for which complexity does increase.
Yeah.
But the question is whether there's some sort of maybe selection mechanisms or other mechanisms like that, which need to be in place for these systems. And they're just as large or maybe much larger class of systems of which the main mechanisms are really sort of, you know, grinding down complexity. They're washing out complexity so that complexity is lost.
Yeah.
And I have no idea how to even sort of think how general these classes are and how we should compare them.
Yeah.
Can you help me a bit more?
Not much, but so I think I agree with pretty much everything you said there. I don't think it's as general as the second law. But there are like a lot of special science laws that are even like more specific that we still, I don't know, as philosophers of science are often inclined to just say the ceteris paribus laws. And I do think that there's at least this generalization that is across several different domains where we do see this robust trend. And I think it would be great to have a theory of why that is. You know, like in general, if we find a planet that's inhabited, should we expect that it's gotten more complex over time? You know, probably. If we wait a while, should we expect that we're going to see more kinds of things in the universe in general, like even if they're not alive? I think probably. How high those probabilities have to be, I don't know. I mean, it would be nice if we had a quantitative answer that said 70% of stuff, you know. And so I don't have much more to say than that.
Okay, very quickly, just your final question.
So you mentioned a problem like with your view, but I'm not sure that it is such a problem as you said. You mentioned, like, let's say partitioning phase space according to these extra variables.
Yeah.
It's like, okay, how do we know if the Mentaculus setup will actually give us the right result somewhere else? But let's say we introduce a new variable, stripiness, we want to get a handle on zebras.
Yeah.
You would need to actually, let's go coin toss it. Got something very obviously 50-50.
Yeah.
So you've got people like Strevens,
Yeah.
They have the whole method of arbitrary functions things. And the idea is that if systems are chaotic, right, and small changes in the initial setup, in the initial kind of launching configuration of a coin, if they're going to kind of small changes in that going to lead to heads, then tails, then heads, it kind of varies very wildly. Well, then actually all the initial distribution from the initial state of the universe needs to deliver is just non-conspiratorial, reasonably smooth distributions. And then you're just going to get kind of stable probabilities for any given kind of system. So it kind of looks like actually you would need, I think that, I think that the finish line for you is much closer than it might otherwise seem. You just basically need to, it's like a kind of non-conspiracy theory. Mm-hmm. So I think getting from the Mentaculus to this thing, I think that will be not so difficult. I think the difficult bit will be kind of characterizing complexity, the other stuff that you said. But I think that kind of worry that it won't translate over, I think there's a good chance to think it would now.
Yeah, I mean, I guess I just have to see it. I mean, a coin seems like the kind of easiest non-thermodynamic thing because of the position, the way it's characterized in terms of positions and velocities. But even that, I could flip a coin and have it land heads every time if I had that skill, which people do, right? And then you're like, oh, but that's conspiratorial. I don't know, right?
That's a header plus coin system.
Yes.
Special
right.
type of.
Yeah, exactly. Yeah. So I mean, my complaint in general about the Mentaculus project is that there's a lot of look at thermodynamics. It works so well, and so on, right? For everything else, all the special sciences will get all the probabilities out. And I think just saying, oh, as long as it's not conspiratorial, you should. I'm just skeptical. I just would need to see the pieces kind of connected better. And I think that the fact that we don't see the statistical mechanics results going forward in an obvious way suggests that the very same explanation they've used to get all the right thermodynamics results will not carry over. So it's kind of a potential argument against the generalization should just go through because it doesn't go through just conditionalizing on a present state forward.
Thank you.